Everyone, and we are back, and we are going to get into our exam 1 solutions for our practice exam. So let's go ahead and let's get started. So I'm creating a metal polymer composite. So I know that I have a fraction of my fiber, which is equal to 0.75. My fraction of my matrix is equal to 0.25. I am told that this fiber epoxy composite, I don't really know what the Young's modulus is for the whatever the metal or the polymer is in this problem. But I'm told that the fibers are aligned with the 3 direction. So 1, 2, 3. So we have fibers that are aligned essentially in this 3 direction. So we have a composite that's a transversely isotropic material. So let's start to kind of figure out what we have here. So I've got my E sub 3 is going to be equal to fraction of the fiber times the Young's modulus of my fiber plus fraction of my matrix times the Young's modulus of my matrix. My Young's modulus in the 2 direction, and I know that S33 is going to be equal to 1 over E3. And E2 is going to be equal to E1, which is going to be equal to 1 over fraction of fiber over E fiber plus fraction of matrix over E matrix. Now, I have a transversely isotropic material, so I am going to look at my stress tensor S, and that is going to be, actually, let's zoom out a little bit more. So I'm going to have an S11. Let's see what else we've got here. So we've got fibers aligned in the 3 direction. So I'm going to have some component that's in the S12 direction. And that is going to be unique because in the 1-2 plane, I'm always transverse to the fibers. I'll also have S13, and also, you could just plug this in here. Or notice I'm doing S11 and S12 is the same because my Young's modulus is the same. And my S23 and my S13 are effectively going to be the exact same because they have some component that's in or aligned with the fibers. So that's going to be S13, S13, and then S33. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, S44. Again, what does the 4, stand for? That's the 2, 3. So 1, 2. Some component in the 3 direction. My S55 will still be S44. 2, 3, 4, 5, and then finally S66 is 1, 2, so that is going to be unique. So that is my compliance tensor. So let's go ahead and continue with this problem. I'm also told that we basically measure the stress straight when the material is 81 degrees clockwise on the one axis. The ratio of the Young's modulus, so E3 is equal to E3 over E1 equals 19.377, and we could also kind of equivalently say that my effectively, we know that S11 is equal to 1 over E1. So effectively, I'm looking at S11 divided by S33 is also equal to that. So I'm given stress values in pascals, strain, reduced units. Again, be careful in case I give it to you in non-reduced units. So let's go ahead and start to solve this problem. So let's go ahead and let's zoom in while we're at it. Not 200. Yeah, 125 is good. So make sure we have these values kind of all ready to go in your notebook. I've got my stress there. My SP1 is going to be equal to T strain 1 dot, I need to actually figure out, actually I have it here. I'm going to steal from another notebook just because I know it's not going to be super exciting for you to see me type these out. So I figured I'd save the audience, and I'd have this ready in your notebook too for a transverse isotropic material. This is going to be my S naught. So S naught dot inverse of T stress 1 slash dot theta goes to, again, this is going to be minus A1 because it's clockwise, slash that n, slash full simplify, and SP1, we've got that. So now I'm just going to go ahead and solve. EP1 set equal to SP1 dot sig 1. And I've got these values. So I've got S44. Let's go ahead and pull these out. I've got S66 as well, but otherwise it's a little bit of a mess. Now, I could play around with trying to do rotations and try to solve the rest of these values, but luckily, I do have this equation here that is going to give me S33 in terms of S11. So I've got my equation here, so I can go ahead and let's solve for S33 and S31 because one equation, 2 unknowns, but we actually know how to solve this one because we had that nice fancy ratio, which we just said previously. So let's go ahead that S11 divided by S33 set equal to 19.377, which we're given in this problem. Solve, and we've got our values. So that's my S11, so it equals here. I've got my S33, got that equal to here. And now, with all the rest of those values, we've got my S12 and S13, and we are good to go, and we are basically done here with this problem. For the most part. We still have to answer actually the questions, but let's do here. So let's see what the question's actually asking us. So this one wasn't too bad, too straightforward. So remember, just set them equal, see what you can pull out, see which equations you could solve for, see if there's relationships. If not, try to rotate or see what other stresses and strains are given. So sometimes you could be able to rotate, but if you're given different stress states in exercises, I would try to solve those first and then iteratively plug and chug and solve them for them. So what's my Young's modulus in the 3-3 direction? Well, it's just going to be 1 divided by S33. S411, 1 divided by S11. So got those values there. Right at the full compliance and stiffness tensor, so that would be my, where is it? So I could do my SP1, my stiffness. Again, that would be in that state of that 18 degrees. If I wanted my S naught, it would be equal, actually I have my S naught here, so I could look at this in matrix form. I could also do it in inverse S naught matrix form. So that would be my stiffness compliance right here. Where else? Young's modulus 3-3, 1-1, compliance stiffness, write out the stress and strains for a 65 rotation counterclockwise around the one axis. That one is pretty straightforward because I can actually go ahead and, so let's go ahead and pull back over here. So I've got the stress, basically stress state values for an 81 degree rotation clockwise around the one axis. So if I want to go from my initial steady state, I have to go minus 81, excuse me, or actually plus 81, and then I'd have to add an additional 65. So I can do, for example, my sig. So again, it's the 65 counterclockwise. I can do sig 65 equals T stress 1 dot sig 1 slash dot. I need to first go, I need to add 81 and I need to add 65. So slash dot theta. That would be helpful. There we go. And for the strain, the exact same thing. So again, hopefully these problems are getting a little bit more straightforward. Again, the key thing is identifying what's your tensor and then going forward with that. So on the exam, just be careful. Again, what are you given? Solve iteratively, see if you can make rotations, and then again, tackle each stress state and corresponding strain state procedurally, so systematically, effectively, and then you'll be good to go. And make sure, again, be careful. The one thing, reduced notation versus tensorial notation. So make sure, where do you have to divide by 2, multiply by 2? So that's the key thing. All right, let's go ahead and we will move on to the next problem, which gives us our anisotropic material. So again, another compliance tensor that we need to kind of solve. Thanks. Have a good one. See you in the next problem.